Hi, this is a pre-recorded lecture to go over the mock exam. I'm going to do this in two parts. I'm going to do the first half of the questions, effectively 2 to 11, and then a new video to record 12 to 21. So let me just start formally with question 1. In my case, I can certainly affirm that I will not give or receive any unauthorised help on this exam, and certainly all the work will be my own. So that is true. And let's go on to the mathematics. So inevitably we find a question on recurrence relations. This mock, as I said, as I wrote, is based on the May 2019 exam. So this question here is easy in the sense that the recurrence relation is homogeneous. So we just have to understand how to solve homogeneous equations like this. So one writes down the associated or considers the associated polynomial, quadratic polynomial. This is a second order equation, and it's lambda squared minus 2 lambda minus 8. That factorizes as lambda minus 4 times lambda plus 2. So the roots are going to be plus 4, which you see here, and minus 2, which you see there. So the correct general solution is given by part B. In A, the roots are written with the wrong signs, so that's wrong. So we now know that A is false and B is true. And as it happens, that's enough to find the solution of the quiz, because if you just go through all the possibilities, A is not true, B is not false, and in the last one, A is not true. So the only possibility left is that C and D are both true. Now, it wouldn't normally be quite that easy. I think I should have written false here. So one would normally expect to work out one other statement in order to answer the quiz. So let me just tell you in this case, since we sort of did this backwards, let me tell you why C and D are in fact both true. Well, first of all, when you have initial conditions, two initial conditions, you would expect to find a unique solution. So it's just a matter of checking whether that unique solution also satisfies A2 is equal to 2. And it does in this case. That's just a calculation. You find out, I think, that C is a 6 and D is minus a 6. So that means that C is actually true. And what about D? Well, D is even easier because you can just take the zero solution. This is a homogeneous equation. So you just take the sequence, all of whose terms are 0. A n is 0 for all n, obviously satisfies D. In fact, I think I missed that myself. It turns out because plus 4 is a root, you can take A0 to be anything and you will find a solution that satisfies this. But in any case, the correct answer is both C and D are true. Okay, let's go on to the next page and see the next question, which is actually another recurrence relation. In fact, it's almost the same one, except that we've made it non-homogeneous. There's a non-homogeneous bit, forcing term, as I used to say, on the right-hand side, 9n. Now, we already know the roots of this left-hand side, the homogeneous part. If you didn't spot this as the same as in question 2, you'd quickly discover it when you wrote, if you were to write down the polynomial. The roots were 4 and minus 2, so the important thing is 1 is not a root. So we would expect to try as a particular solution a constant times n plus another constant, because one would need to try a polynomial of degree 1, but nothing more fancy, because 1 is not a root. So if we go through these statements, you see that the first one here is definitely wrong, because 2 is not a root, so we would never expect to see a solution which involves 2 to the n. So the first one is wrong. There exists a solution for which A1 is equal to A2. Well, that's definitely true because, as I said before, with these sorts of equations, you can always specify two initial conditions. So here we're not even quite doing that. We're just saying that A1 is equal to A2. We could set them both equal to 1, in fact. But this is therefore true. So the correct answer should just be that one. Okay, so maybe, if we're doing this quickly, I can just go on at this point if I'm confident enough to know that's the correct solution. But let me just explain why the others are false. This is not a homogeneous equation, so you don't expect to be able to add solutions. It won't be true. In fact, it definitely won't be true that if you take two solutions and you add them, the sum will be, term by term, will be a solution, because it won't. It will give you 18n and not 9n. So that's definitely false. As I said before, you don't expect to see n squared in a particular solution because 1 was not a root. So this is false. Now the last one is, of course, the order could have come up differently. But in this case, the last one could be true. I mean, it's not a silly statement because one would have to do a calculation, but it turns out, I think, that a particular solution is actually some constant times n plus 0. So this is actually not true, but that would need a calculation. In any case, and you may have, these could be shuffled, so you may have come across this first and you may have wanted to go down the other ones before actually doing that calculation. Anyway, that's the correct answer. Next page. So here we have a question about graphs, but there's no picture here, so you have to know pretty well what K5 is. And again, with this sort of question, you need, on the whole, I think you need, unless you happen to be lucky and spot the answer that's correct here, you would need at least to evaluate 3 of these statements. Now, so you should look at them all, not necessarily in the order given. So, in my case, I would say, well, part D, if you look at part D, this is definitely correct because you probably should know that of the Platonic graphs, the only one that has vertex degrees even, and that's what you need for Eulerian, is the octahedron. So the octahedron is Eulerian. All the Platonic graphs are Hamiltonian. You can check that if you've forgotten from the table in the notes. And certainly the octahedron has 12 edges, so it's pretty clear that D is correct. So if you go through the possibility, that will eliminate some possibilities. C and D are not false. So it eliminates one possibility. Let's go back to part A. Maybe I can even draw K5. So here's an attempt to draw K5 based on a pentagon. And then we'll see what happens when I remove one edge. Okay, so there is K5. Now we're going to remove any one edge. All the edges are somehow equivalent, so it doesn't matter. But let me remove, I don't have an eraser, but let me remove this edge here and try and imagine colouring the 5 vertices of that graph. Well, the key point is that in this case, you can use the same colour for these 2 vertices. These 2 vertices here, this one here, this vertex here, and this vertex here, these can be given the same colour because they're not adjacent anymore. And then you just have 3 colours on the other vertices. So certainly 4 colours will be enough, and you're going to need 4 colours. So A is actually true. And let's see what that tells us. So the first one is A is true. We still haven't, well, no, we're lucky enough actually, because I started with D, we can actually say what the solution is. So the correct answer, I mean, even if one of the others was true, you're going to obviously get full marks since you can only select one. A and D are both true. So you get that because we sort of skipped to D. I mean, you need to look at all the parts to see maybe the easiest way of doing it. Depends what you may or may not find easier to solve. So why, in fact, what was the other thing? Why are let's see, what are the others? What about B? Well, B is definitely false because if you contract two edges, you're still going to have 3 cycles. And bipartite graph, that's a fairly strong condition. It means you can colour it with 2 colours. And even if you contract 2 edges and combine vertices, it won't become bipartite. So B is false. C is actually true because any connected graph with n vertices and n minus 1 edges is a tree. It's a tree, and therefore it's planar. Any tree is planar. So C is actually true, but B was false. So anyway, the only answer is A and D are true. That's the correct answer to that question. Next one. Now this is an attempt to test theory here, in the sense that we're being asked to try to understand how one could prove the fact, well-known fact, that any 2 adjacent Fibonacci numbers are coprime. So this is the statement here that is certainly a true statement, and we're being asked to prove that. Let's outline this again. So this is a statement we have to try to understand how you might prove. Now, 4 statements are given here, 4 facts, they're all true, but which ones are useful for proving this statement? Well, the first fact, the greatest common divisor of 2 adjacent Fibonacci numbers can be done in a certain number of steps. Well, we did do that excuse me, in a lecture, but that's not really relevant here. I mean, knowing the number of steps doesn't really help you find what they are or to understand this statement here. So actually, A, I think it's fairly clear, is not terribly relevant. What about the greatest common divisor of F1 and F2 equals 1? Well, being coprime means that the greatest common divisor of these 2 Fibonacci numbers is 1, and this is just a special case. This is a special case when n is 1. So that looks a bit like induction. This is a special case, so we would expect this to be relevant. Fn is the closest integer to this quantity. Well, that's not really much to do at the moment with greatest common divisors, so we put that on hold. What about part D? Well, if an integer divides both of these, then it will also divide Fn minus 1. Well, division by integers is very relevant to being coprime. So in fact, this is also relevant. I hope it's fairly clear that B and D are the most relevant too. So at this stage, even without a full understanding, one could click B and D. In fact, if you think about it, this is going to lead to a proof by induction, because if an integer divides, we're looking for all the divisors. We're trying to show that the only divisor of Fn and Fn plus 1 is 1. So if we do have an integer that divides both of them, then it will divide the preceding one, but then it will divide both Fn and the preceding one, so we can go down to the Fn minus 2, and you can keep going by induction until you get to F1 and F2. These are, of course, both equal to 1, so their greatest common divisor is 1, and that completes the proof effectively by induction. So that's that question. Next question. Okay, so this is a more geometrical question, but it's clearly going to be based on Euler's. It's going to possibly relate to Euler's formula, because we're talking about plane diagram. So when we have a plane diagram, not only do you have vertices and edges, but you can also talk about faces. You can only do that for a plane diagram. the faces are essentially the regions including the outside one. And we know that in that case n, see if I can write this down, we know in that case that n minus the number of vertices minus the number of edges plus the number of faces is equal to 2. That's Euler's formula. Well, unfortunately, almost all of these satisfy that formula. I think one doesn't. 10 and 6 minus 15 is 1, so this one is certainly false. But all the others do satisfy this formula, so we have to actually really understand the question, I think, to go on. And this is the sort of, to solve a question like this, you just really have to understand what it's telling you. So we have k straight lines, but in this quiz version, k is 5. If you look at the exam, I think you'll find a more general statement is required. But here we're just reducing k is 5. So if you like, you can sort of think of, if we go back to the general, what would happen for general values of k, and just do the case k is equal to 5. You can almost do that by hand. In fact, I can maybe even do it on screen. So we have 5 straight lines, and we're constructing out of that a graph. So here are the 5 straight lines. I have to try and draw them sufficiently generally, if I can manage. Well, no problem if there were 3. So let me just stop for a moment. If k were 3, the idea is you only look at the finite segments. So you only really, in this case, you just have the triangle here. There would be 3 edges, 3 vertices, and there would only be one region because you're forgetting about all these semi-infinite segments. So one region outside, one region inside. And so 3 vertices, 3 edges, so they cancel out, leaving 2 regions, which is 2, which is correct. But then we've got also, we need also a 4th line. So I don't know if I'm going to manage this. Here's the 4th line. We've now got 4 regions, 3 finite ones on the outside. And we are going to need a 5th line. So let's see if I can put that down there. I think that's okay. So how many regions have we got now? We've got 1, 2, 3, 4, 5. Now let's see. Let's look at this carefully. Is my drawing accurate? Have I left anything out? I didn't count them, did I, properly? So we've got 1, 2, 3 there, 4, 5, 6, 7. So actually there are 7 regions. Or we could actually count the, well, let's see, there are two possible answers here with 7 regions. How many vertices do we have? Well, we certainly have more than 5. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we now see here we have the correct answer. It's that one. I mean, you can argue a bit more generally here. The point is, how do you count the number of vertices? Well, since you've got 5 straight lines, each straight line will intersect 4 other straight lines. So there are going to be 4 vertices on each line. Okay, so you think that might give you 20 vertices. On the other hand, each vertex is on 2 lines. So you half that number, 20, and you get 10. So I could say more about this question, but anyway, that's the correct answer. Next one. You can, of course, ask me if you don't follow my explanation. There's going to be a live session on Friday. Look on Keats, or you can contact me through Teams at other times this coming week. So let me just go on with the next question. So here we have a graph. Now, I don't think you have to sort of copy all these graphs on a piece of paper. You may want to do that. You certainly have time to do that. This is a grid, so you can certainly copy the grid I wouldn't waste time copying all the numbers, but in fact, you should be able to answer this question by just sort of looking at the graph, which you can see even on a tiny screen. So in this case, this is about evidently something to do with Kruskal's algorithm, maybe because we're looking at minimum spanning trees. So how would you find, here, let's just go through in order. The sum of the weights of the edges of any minimal spanning tree, that's the total weight of the minimum spanning tree, is 41. Well, all you have to do is find one. They all have to have the same total weight and see whether it's 41 or not. So you apply Kruskal's algorithm, which tells you, first of all, you have to choose edges of smallest of minimal weight, providing they don't give you a cycle. So we can certainly choose all the edges of weight 1, no cycles there. Then we look at the ones of weight 2. Well, I could, for example, choose these. Doesn't matter what order I choose them in, it will be correct, but I mustn't have a cycle. So having chosen this vertical one, I can't choose this horizontal one, but I can choose the other twos. So then I go on, I have to add weights of order 3, of weight 3, edges of weight 3. So I could choose these two. If I do that, I can't choose that one, but I can choose these two. And I've almost finished. I now need 2 edges of weight 4. It doesn't matter which two, I could choose those two. Now you have to add up the various weights. So you've got 7 weights of 7 edges, of weight 1. We have, how many 2's do we have? We have 6 edges of weight 2, that's 12. How many edges of weight 3? We've got 1, 2, 3, 4, that's another 12. And finally, we had only 2 weights of 2 edges, of weight 4, none of weight 5. So the sum of those is 32, 39. So this 41 is wrong. It should have been 39. Any minimum spanning tree, the weights will add up to 39. So A is false. We're on our way to finding the correct answer. Any minimum spanning tree has 19 edges. Well, that must be true because there are 20 vertices, 4 times 5, 4 columns, if you like, of 5, or 5 columns, 4 rows of 5, 20 edges. So there are 20 vertices, so any tree must have n-1 edges, 19 edges. So B is certainly correct. So we now know that A is false and B is true. So this is no good. This one could be okay. C, and we haven't got to C and D yet. A and D are true. That's not correct because A is false. So we still have 2 to decide between. So let's see, there exists a minimum spanning tree that contains exactly 6 edges. Well, in fact, our choice did that. We had exactly 6 edges of weight 2. In fact, I think any choice will have that. So that is in fact correct. Therefore, B and C are correct, and B and C are true, I should say, I guess. And that means we've actually done enough to answer the quiz. Actually, D is also true, if you're interested, because it is true that any minimum spanning tree, you can probably sort of understand why that's true. This is a bit trickier, but it's true. So that's that quiz. Now, this also relates to the same weighted graph, but now we're talking about shortest paths, I think. So in this question, I was too lazy, I think, to mark the fact that this vertex is to be thought of as the start, and this vertex here is to be thought of as the finish. So we're looking for paths from S to F, and the question is kind in the sense it's reminding you that a path means that you can't go through the same vertex more than once, unless it were a closed path, but here it's not closed, so you can't go through the same vertex more than once. So does there exist a path from S to F with 19 edges? Well, the quickest sort of path from S to F would have 7 edges. Okay, there are quite a few with 7 edges. Use of 1, 2, 3, 4, 5, 6, 7. You've got lots of choices. But we're asking for 19 edges. Can we get, that's a sort of longish path. What is the longest path from S to F? Well, a bit of thought will make you realise that you can do this feature here. And how many edges are there? Well, vertically there are 1, 2, 3, 4, 5, 15. And horizontally there are 4. So this is actually true. There is a path with 19 edges. Maybe that's unique, I'm not sure. But anyway, that's certainly true. It's easy. Just have to understand what the question's saying. Then you have to understand what a path is. Then you have to understand what an edge is. That's all you have to do to say that that is true. There are 21 paths from S to F with 7 edges. Well, I showed you quite a few. I could explain in a moment why that's false, but I think understandably one might want to skip that one in doing this quiz. So let's skip that for the moment. The minimum sum of the weights of any path from S to F equals 19. Well, you could apply Dijkstra's algorithm to find a shortest path from S to F. Okay, but to do that, maybe you would have to copy the graph. You could copy the graph. You wouldn't have to copy the numbers. You could just copy the graph and apply the algorithm by looking on screen. But you really don't have to do that, I think, to understand that this is a true statement, because, I mean, the path I showed you, first of all, have the ones across the bottom, then going up, that would be 4 plus 15, that's 19. And then you see, can you do it any more with any shorter? Shorter, of course, means you're taking the sum of the weights and making that small as possible. You might think it would help to go up, straight up to the top here. That's only using 3, but then unfortunately you're stuck with 16, so you still have 19. And if you look at it, actually any of these paths with 7 edges will always sum to 19. And if you add more edges, it's likely you'll increase that number. So actually, this is correct. D is also correct, because the path which is still visible here, if you sum up the numbers, you get 55. Let's just check that. You have 3 ones. You have 4, well, let's say 4, let's do these together. 6 and 4 is 10, so that's 13. 14, another 10, isn't it? Because it's 1 plus 9, so that's 23 up to here. And then we got 4 fours are 16, that becomes 39. And then we're left with 40, 55. So we do get to 55. So there does exist much easier to find that. So there exists a path with total weight 19. 55. So D is actually true. Much easier to prove existence than statements about how many paths there are. I want to explain why B is false. Well, in any case, we don't have to look at B, because we already know in this situation that, what have we got? A and B are true, that's not correct. B and C are false, that's not correct. C and D are true, that's what we proved. So that must be the correct answer. But just for the record, why is B false? Because how do you get a path with 7 edges? Well, if you only have 7 edges, you can't you have to go either right or up. You can't start going backwards. You can't start going down or to the left. So you have to go right or up. Now there are 7 edges. There are 3 ways of going. You can decide when to go up in each of those 7 edges. So you've got to go up 3 positions. You've got to jump up 3 times. So you've got 7 choices of when you do that. You can either jump up immediately or you can wait 1 and jump up. So you're really choosing 3 from 7. And the number of ways of choosing 3 from 7, 7 choose 3, is 35. It's not 21. So there are actually 35 paths with 7 edges. Anyway, that's that. And I hope you're sort of understanding you don't have to work out true and false for all 4 statements. Typically 3 will be enough. If you're lucky, you'll manage by just coming across 2 and finding the correct answer. Next question. Well, at the very beginning of the course, I talked about the Lund algorithm, as you probably know, one of my favourite things, just based on very elementary arithmetic. You just have to understand how this works, and you're told you don't have to memorise this, you're told how it works in this question, you just have to follow the question, like for that question about 5 straight lines. If you just understand what you're being told, then you can just do the calculation and find which is the correct answer. So you just have to do, now these numbers are all very similar, so actually if you do one of them, they may come up in any order here, but if you do one of them, you can probably, if you're clever, work out which, if that's not true, if that's not valid, then you can probably work out which of the other ones is valid. So let me start with let me use that tact for the first one. So let's look at this first number. Now if you read what you have to do, you modify the first and the third and the 5th digits and so on. So let's see if I can do that on the screen. So what you have to do is you have to, let's see, you have to modify, well, first of all, let's add up the digits you don't modify. So see if I can do that. So the digits we don't modify are the even placed ones. So it's 7 plus 2. We only want to see if it's divisible by 10, so I can forget things that add up to 10. So 7 and 2 and 0 and 8, that's 17. And 7, that's 24, 25, 31, 33. So I think that the digits we don't modify give 33, if I can manage to write that down. 33. Now I'll try and just take the other digits, I'll double them. Remember, if the answer is bigger than 10, you subtract 9. So if it's bigger or equal to 10, you subtract 9. So 6 and 6 is 12, that's 3, plus another 3, that's 6, plus 2, that's 8, plus another 2, that's 10. So I can forget about that 10, start again. 6 and 6 is 3. Let me just start again, make sure I got this right. 6 and 6 is 3, plus another 3 is 6. 7, 8, 9, 10, yes, I did get it right. 6 and 6 is 3, plus 2 is 5, plus 6 is 11, let's call that 1, plus 7, that's 8. Okay, so I reckon the sum of these is 41. That's not divisible by 10, so this is false. Okay, this is false. But all we have to do is, if we could subtract 1 in one of the odd placed positions, we'd be okay. And if you just look down the line here, you see that this one here is looking pretty good, because this is identical apart from the 1 in the 4th in the even position here. So by reducing that 1 to 0, this would become 40 mod 10. Remember, I've reduced some 10s already, so the sum isn't 40, but it's 40 mod 10, so that's okay. So actually the correct answer is this middle one. And you see, I didn't have to check them all. So there we are, that's the correct answer. That's a valid credit card number. Okay, next question. Okay, this looks as though it's about a matrix or linear codes, but it's not. In fact, it's about graphs, because this is the adjacency matrix of some graph. And well, you know, some of the here it's a simpler sort of quiz. We just have to find the true statement. So the true statement. So some will be very easily seen to be false. So how many edges are there here? Well, we know how many vertices there are. There are 10 vertices, because this is the adjacency matrix, which means you use the vertices to label the rows and columns. It's a symmetric matrix, because we've just got an undirected graph. So if an edge goes from A to B, it goes from B to A. So that's why it's a symmetric matrix. There are no numbers down the diagonal, so there are no loops. So it's certainly a simple graph. Is it a regular graph? Well, you have to see what's the vertex degree? So for vertex number 1, if we look at column 1, the numbers add up to 3. So there are 3 edges coming from vertex 1, so that has degree 3. And if you look at it, every column has some adding up to 3. So actually, all the vertex degrees are equal to 3. So this is indeed a regular graph. So this is rubbish. It's simple, but it's not regular. Perhaps I should redo that. So it's simple, yes, but it's not regular. But it is regular, so that's incorrect. How many edges are there? Well, if there are 10 vertices and each of degree 3, that means the sum of the vertex degrees is 30, but you have to half that. So 30 edges is wrong because we forgot to half that. In fact, I've been a bit cruel here, because many students last year did actually say 30 edges, but they forgot to half it. So this is false. Now, what's left here? Can we try and narrow this down without doing absolutely everything? Well, I would say that the last one is probably the easiest to dispense with, because the complete graph K5, which I already drew in this talk, has all the vertices have degree 4. So even if it's homeomorphic, even if there's a subgroup homeomorphic to K5, you couldn't actually reduce those vertex degrees. All the vertex degrees are 3 and not 4. So here we'd be talking about vertex degree 4 for K5. So you couldn't possibly go from 4 to 3. Even if the things were homeomorphic. Homeomorphic just means you can add or subtract, well, in this case, add vertices of degree 2, but that doesn't affect the fact that you'll be left with ones of degree 4. So this is false. Now, you know, at this stage, if you're in a hurry, suppose you're in a hurry, you've got to finish off within the 3 hours. How can we choose one of these? Well, maybe this is perhaps a little bit tricky, but what you should really spot here, I think, is the really special nature of these blocks here. These are symmetrics, that's indicating the same thing. We just have one edge going from vertex 1 to vertex 6, and one going from vertex 2 to vertex 7. So if we remove these 5 edges, 5 particular edges, if we remove these, then this whole thing becomes the zero matrix, and this whole thing becomes the zero matrix. And then the thing drops into 2 blocks. So that means the graph will just have 2 components. Vertices 1 to 5 won't be connected in any way to vertices 6 to 10. So actually, the correct answer is this one. And it turns out that these 2 components, if you look carefully at these blocks, this is just, each vertex has degree 2 here. So this is actually corresponds to C. These blocks correspond to the cyclic, the 5 cycle. It's just that the vertex are taken in a different order. So vertex 1, you see, if you look at this, vertex 1 there's an edge to vertex 2, and then from vertex 2 you also get to vertex 3. I know, actually it looks pretty good order, doesn't it? Vertex 3, you get to vertex 4, so it's very natural order, in fact. and vertex 4 you get back to vertex 1. So it is really just a 5 cycle. This matrix just represents a 5 cycle. So the correct answer, so this is false because the not is false, it's incorrect. And so the correct answer here is this penultimate one. Okay, so the last question of this half lecture. So we'll look at the question 11, which actually, questions 2 to 11 were actually based on section A, as it happens. I would recommend you try and do the paper version of the May exam from last year, because the sort of things that were being asked were slightly different, and I think it will help you understand better what's going on. And you'll sort of also understand how the difference in nature between the paper questions and the multiple choice questions, although they're based on the same material. So here we are, last question, so to speak, from section A. So based on the sort of latter part of the lecture course, we have 4 statements to consider, and we can look at them in any order to begin with. So we have here a number n which is declared to equal 101. So it's just really writing n is just an abbreviation for writing 101. Now, to avoid any confusion with binary, because 101 could in fact be a number in binary, probably this wouldn't be on an honest exam because it'd be too confusing, but I have written 101 to make it clear this is not a binary number, it's a decimal number. So n is the 101. And x is a positive integer which is not divisible by 17. Well, is it true that x to the 16 is equal to 1 mod 17? Yes, of course it's true. That's Fermat's little theorem. Provided x is not divisible by the prime, 17 of course is a prime number, so this is Fermat's little theorem. Of course 17 is a prime number, and provided x is not divisible by 17, and that would include 0, this is true. X to the 16, x to the n, x to the p minus 1 is 1 mod p. Now part B is a bit harder, so I'm going to leave that for the moment, and let's go on to the other parts. So the binary expansion of n, well, you can do that very quickly, and you can just test what this number is, actually. Or how would you find the binary expansion of n if you were asked in some other sort of question? Well, 101, you know, what are the biggest powers of 2 that are contained within 101? Well, we only get 64. And then we can get 32, that will give 96, we're almost there, and we just need a 5. Well, 64 is 2 to the power 6, so that would be a 1 followed by 6 zeros, which here we do have sort of 6 things after the 1, that's okay, and then the 32 would be 1 followed by 5 zeros. So the first 2 ones are good. But you see what's left here is not 5, it's 9. So it should have been the third one is in the wrong place. It should have been 1, 1, 0, 0, 101. 5 is 101 in binary. 101, not this 101, but a different 101. So this is definitely wrong. I mean, that's just a very easy elementary school elementary. So this is wrong. D at this point you probably know is true, because if what the binary is almost the same as that written, and to know how many multiplications you use, that's really a test of whether you know the multiplication by repeated squaring algorithm. And if you do this multiplication by repeated squaring, x to the power 101, you know that you look at the number of digits. Well, if it were 1 followed by all zeros, you'd only need actually 6, strictly speaking, 6 multiplications, because the first one doesn't really, you just have to multiply 1 by 1 or something, so that doesn't really count. So you could actually do everything in 6 multiplications. As it happens, because you'd be squaring 6 times, As it happens, we've got 3 1s here after the initial 1. So that would add 3 more non-trivial multiplications. So you could actually do everything with 9 non-trivial multiplications, which is certainly less than 14. 14 here has been written for sort of safety's sake. Even if these were all 1s, you'd only need 14. So D is definitely correct, unambiguously correct. And that should be enough to actually answer this quiz. So B and C are both false. That's not true. B and C are false. Oh, that could be true actually. So where are we? We still don't have enough. A and B are false. That's not true because A is true. C and D are true. That's not true. A and B are true. B and C are false. So we still need to know. We still have to do a bit more work, unfortunately. So we need to know whether we need to know about B. So I couldn't avoid this. So, well, what do we got? X to the 101, X to the 5. Well, the point here is that if you think about what 101 is, you have to sort of relate it to 5. I mean, you could factor this. You'd take, this is saying x to the 5, x to the n minus x to the 5. So you could take out x to the 5. So you'd have actually x to the 101 minus x to the 5. We're asking, is that 0 mod 17? Well, you can take out x to the 5 as a common factor. That would leave you with x to the 96 minus 1. And the point is that 96 is 6 16ths. So x to the 96, that's x to the 16 to the 6, which is just 1 mod 17. So this is indeed 0, is indeed equal to 0 mod 17. I'll say equivalent to 0 without writing a mod 17. So actually this is true. So this statement is true. I'm fiddly here. That statement is true. So actually A and B are true is the correct answer to this quiz. B and C are false. That's no longer correct because we know that B is true. Okay, that finishes the first part, and join me for the lecture on the second part of this quiz.